The Aissen-Schoenberg-Whitney theorem tells us that the zeros and poles of certain power series are real if and only if a related infinite Toeplitz matrix is totally non-negative. Now the coefficients of these power series are symmetric functions in the poles and zeros. So the entries of this Toeplitz matrix are symmetric functions since they're taken from the coefficients, and that means that there's symmetric functions lurking in this theorem. Let's look closely and see what we can say about them. Right, so recall that the product 1 plus alpha 1z through 1 plus alpha nz equals 1 plus the elementary symmetric function, first elementary symmetric function of the alphas, z, plus the second elementary symmetric function of the alphas, z squared, etc. Where the kth elementary symmetric function in alpha 1 through alpha n is a sum over all sequences of indices I1 through ik, alpha I1 product up to alpha ik. That's the kth elementary symmetric function. Now the Aissen-Schoenberg-Whitney theorem says that the Toeplitz matrix T of 1, E1, E2 up to En is totally non-negative if and only if alpha 1 through alpha n are real and non-negative. Aissen-Schoenberg-Whitney didn't say this, but apparently using what we know about Toeplitz matrices, this Toeplitz matrix is the path matrix of the infinite planar network where we have horizontal edges weighted 1, diagonal edges weighted alpha 1, and then more diagonal edges weighted alpha 2, etc. And finally more diagonal edges weighted alpha n. Now let's change the alpha 1 through alpha n to x's. And ask how can we describe the symmetric functions which are minors of the matrix 1, E1, E2 up to En, 1, E1, E2 up to En, etc. Now the minors are determinants of submatrices, so they're definitely going to turn out to be symmetric functions. In x1 through xn. So here ek is ek of x1 through xn. So definitely symmetric functions, because when you multiply two symmetric functions you get another, and when you add two symmetric functions you get another. When we take determinants we're adding products. So one way to explain what they are is their weights of path families in the planar network. Well, basically this planar network, but let me erase the numbers alpha and make them x's. So again we've got horizontal edges weighted 1, and then we have these diagonal edges weighted x1, 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 x2, 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 etc. up to xn, 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 and continuing forever downward. I'm thinking of the sources as being numbered from top to bottom here, since this continues infinitely. I guess I could do them bottom to top and write the dot 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 on top, but that seems a little bit unnatural to me. Let's look at an example. So if we take a 2 by 2 matrix, I'm going to pick the smallest one that I think is not trivial. I'm going to look at the 2 by 2 matrix E2, E3, and then 1, E1. Now let's say n equals 3, so there's 3 variables. It's the smallest number of variables for all of these. Makes sense. So this determinant is let's see, E2, E1 minus E3 times 1, which is E2 is x1, x2 plus x1, x3 plus x2, x3. E1 is x1 plus x2 plus x3, and then E3 is x1, x2, x3. So this is, let's see, x1 squared x2 plus x1 x2 squared plus x1 x2 x3 plus x1 squared x3 plus x1, x3 squared plus x1, x2, x3 plus x2, x3, x1, that's plus x1, x2, x3 plus x2 squared, x3, and x2, x3 squared, all of this minus x1, x2, x3. So we'll basically just cancel one of these and cancel that. And we get, let me write shorthand m21 for all the monomials where the exponent sequence is a single 2 and a single 1. And then m111 for all the monomials where the exponent sequence is 1, 1, 1. So in general, where m lambda equals the sum of monomials in x1 through xn with exponent sequence lambda 1, lambda 2, etc. Just shorthand, so I don't have to write all of these. One variable squared, one variable to the first monomials. All right, now if we have three variables, I guess we can use this planar network. I'll just change the n to a 3. So we should be able to find some path families. I guess there's going to be 8 of them. With these weights. So let's see. So we can pick the sources and the sinks so that the weighted sum of paths from source 1 to sink 1 is E2, and the weighted sum of paths from source 1 to sink 2 is E3, etc. So actually the 1 should be easy. So if we pick, let's say S2 to be here, so we're going to be looking at a submatrix, a subplanar network here. And sink 2 is here, then we've got the 1, because there's one path across. Oh, actually that should be sink 1. And then I think we put sink 2 there, because we want the first elementary symmetric function to be the sum of weights of path families from source 1 to sink 2. Then we can take the x1 path, or the x2 path, or the x3 path. That'll be x1 plus x2 plus x3, which is the first elementary symmetric function. Alright, so I think I've got the second row down. Now for the first row, from source 1 to sink 1, I want the number of the weighted sum of paths to be the second elementary symmetric function. So I think I should put it here so that when I go down 2 levels, I'll take one variable and then another variable. These edges are slanted, so once I take the x1 edge, I can't take the other x1 edge. So I can take x1, x2, or x1, x3, or x2, x3. So that is the second elementary symmetric function. Alright, so if we want a non-intersecting path from these sources to those sinks, let's see if we can get the one that has this weight. So we have x1 squared, and no path can to take an x1 edge twice because of the way they're slanted, so that you finish one too late to take the next. So I guess both paths have to take an x1. And then an x2, well, the first path has to go down one more level to get here. So there's a path of weight x1, x2, and here's a path of weight x1. Maybe we can do one more. So what if we wanted to get x1, x2, x3? I guess there should be two path families that have weight x1, x2, x3. Well, we could take this path again. That'll be an x1. And then we can make this path take an x2 edge and an x3 edge. And just for fun, let's see how we can do that with another way to get x1, x2, x3. What if we have the second path take the x2 edge, and the first one take x1, and then x3. Those are far enough away so that it won't crash. So here's another path family of two paths. Oops. x1, and then x3. So those are three of the apparently 8 path families that go from sources 1 and 2 to sinks 1 and 2 without touching. So this one has weight x1, x2, x3, and the green one also has weight x1, x2, x3. And the red one has weight x1, x1, x2. All right, so that's how the polynomial power series work. The power series where the coefficients are just coefficients of a polynomial. So we have a product of 1 plus alpha I z. Now let's look at the products of 1 over 1 minus beta I z. So recall that, oops, it's too low. Here we go. So recall that 1 over 1 minus beta iz times 1 over 1 minus beta 2z, product up to 1 over 1 minus beta nz, equals 1 plus h1z plus h2z squared plus h3z cubed, etc. It's an infinite power series where hk, which is hk of beta 1 through beta n, is a sum of products beta I1 through beta ik, where I1 through ik is a weakly increasing sequence. We call this the kth homogeneous symmetric function in beta 1 through beta k, in beta 1 through beta n. So the Aissen-Schoenberg-Whitney theorem says that the Toeplitz matrix 1, H1, T of 1, H1, H2, H3, etc. is totally non-negative if and only if beta 1 through beta n are real non-negative numbers. Equivalently, this power series has only real poles if that matrix is totally non-negative. Now apparently from what we know about Toeplitz matrices, T1, H1, H2, etc., is the path matrix of the infinite planar network where we have horizontal edges having weight 1, vertical edges having weight beta 1 in a column, and then we've got another column of vertical edges weighted beta 2. The vertical edges are all oriented downward, etc. There's n columns, and then the nth column has vertical edges weighted beta n. Alright, now again let's change the betas to x's. And look at the symmetric functions. Which are the minors of the infinite Toeplitz matrix of homogeneous symmetric functions. Again, the minors are definitely going to be symmetric functions because every minor is a determinant of a submatrix, so it's a sum of products of symmetric functions, and symmetric functions are closed under sum and closed under product. So again, these minors are weights of non-intersecting path families. In this planar network where we change the betas to x's. So let me just use this again and I'll change the betas to x's. So we have a column of vertical edges weighted x1 each, a column of vertical edges weighted x2 each, a column of vertical edges, well, for every variable up to xn. So for example, if we take, let me take a similarly small submatrix. We take the determinant of the submatrix whose entries are h2, h3, 1, h1. So this is, let's see, h2 is the sum of all products of variables 2 at a time where we can repeat the variables. So x1 squared plus x2 squared plus x3 squared plus x1, x2 plus x1, x3 plus x2, x3 times x1 plus x2 plus x3 minus h3. So minus the sum of products of all variables 3 at a time where we can use variables at most 3 times. So x1 cubed plus x2 cubed plus x3 cubed plus x1 squared x2 plus x1 x2 squared, etc. up to x2 squared x3 x3 x2, x3 squared plus x1, x2, x3. Alright, so I did this on scrap paper, and I'm not going to bother doing the whole thing out. This turns out to be well, actually I guess we can do it out. So if we use this the monomial notation, then we can see that here we get every variable cubed once. So m3. And then if we look for one variable squared times another variable, we can do that in two ways. So for instance, x1 squared x2 is going to come up here, and it's going to come up when we multiply x1, x2 by x1. So we're going to get 2m21. And then if we look at all the ways to get a product of all three variables, that's going to happen when we take x1, x2 times x3 here, or x1, x3 times x2 there, etc. So there's three ways to do that. And then we're going to subtract m3 and m21 and m111. So no m3s. One of these 2 ones goes away. And then one of these m111s goes away. So we have 2 of those. Which happens to be the same as last time. Alright, so just for fun, let's find a couple path families that have weights here. So we need things like x1 squared x2, x1, x2, x3, x2, x3 squared. And if n is 3, then let me replace the n's here with 3's. And let's see where we're going to put the sources and sinks. So I think pretty much in the same places. Because we want to have exactly one path from source 1 to source 2 to sink 1. From source 2 to sink 1, there's exactly one path. From source 1 to sink 2, there's h1 path, which is the same as e1. So every variable, x1 plus x2 plus x3. And then if we put the first source here, then to get from the first source to the first sink, we can take any variable twice, or any one variable followed by another variable. So any pair of variables, including any variable twice. So that's precisely what h2 is. And then if we want to get from source 1 to sink 2, we're going to go down 3 levels. We can take any variable 3 times, or any variable twice and another one once, or any 3 different variables. So that's exactly h3. So this is the planar network with these 2 sources and these 2 sinks. The subnetwork is the one that has this as its path matrix. So if we look for some non-intersecting paths, so here's one. That has weight x1, x2 squared. And another one is, you can take the x2 edge here, and then maybe the x1 and x3 edges there. Those don't intersect, so that has weight x1, x2, x3. And maybe one more that has weight x1, x2, x3. We can't take x3 on the bottom because then the top path is going to crash. The top path definitely has to get here to get to T1. So let's make the bottom path go down on the x1 edge, and then the top path is going to go down on the x2 edge and the x3 edge. So that one has weight x1, x2, x3 also. All right, now hopefully what we've done raises some questions. Question 1, why do we get the same answer when we took the determinant of E2, E3, 1, E1, and the determinant of H2, H3, 1, H1? And 2, so I use this shorthand with these monomial symmetric functions. How are these monomial symmetric functions related to elementary symmetric functions homogeneous symmetric functions and, let's say, non-intersecting path family symmetric functions? And question 3, is there a shorter name for non-intersecting path family symmetric functions so that we don't have to keep saying all that? And those are 3 questions that we will look at in more videos. The end.